This scene deals with the subject many fathers find so difficult.
Welcome to Podcast V0.1, where we break down the latest research and tools for curious engineers. Today, we're diving into the high-stakes world of particle physics and cloud-native security. How does one of the world's largest scientific experiments, CERN's compact muon solenoid, or CMS, protect its critical computing infrastructure? It turns out they're leveraging a powerful trio of well-known cloud-native security tools, network policies, Open Policy Agent, and HashiCorp Vault to lock down their vital Kubernetes clusters against modern threats. This isn't just theoretical. It's a real-world implementation detailed in a recent paper titled Implementation of New Security Features in CMS WEB Kubernetes Cluster at CERN. So let's set the stage. The CMS experiment at CERN generates colossal amounts of data from particle collisions. Analyzing this data requires a complex ecosystem of services for things like data management, discovery, and bookkeeping. These essential central services run on a dedicated Kubernetes cluster called CMSWEB. Migrating these services to Kubernetes and containerized applications already brought huge benefits, like faster release cycles and lower operational costs. But as any engineer working with Kubernetes knows, while powerful, it isn't secure out of the box. Default Kubernetes allows fairly open communication between pods, and basic secrets management is fundamentally weak. Native Kubernetes secrets are merely base 64 encoded, not truly encrypted at rest by default, nor dynamically managed. For an experiment like CMS, where service availability and data integrity are absolutely crucial, these gaps are unacceptable. A security breach could disrupt operations, compromise sensitive configurations, or even damage trust. The potential consequences, data leaks, service downtime, reputational damage, are severe. Faced with these challenges, the CMS team decided to significantly bolster the security posture of their CMS WEB cluster. They didn't rely on a single silver bullet. Instead, they implemented a layered defense strategy using 3 distinct but complementary technologies, each addressing a specific security domain within Kubernetes. Let's break down this trio. First up, network policies. Think of these as internal firewalls operating within the Kubernetes cluster, specifically at the pod level. By default, any pod can talk to any other pod, regardless of namespace. If one service gets compromised, an attacker could potentially move laterally across the cluster to attack other services. Network policies prevent this. The CMS team implemented network policies using Calico. For context, Calico is a popular CNI, or Container Network Interface plugin, which is responsible for managing networking between containers and, importantly here, supports policy enforcement. These policies define rules based on things like IP addresses, ports, and crucially, Kubernetes labels, specifying exactly which pods are allowed to communicate with each other. For example, a backend service in its own namespace might only allow incoming traffic, known as ingress, from specific front-end services running in a different namespace, like an authentication proxy. All other traffic, both incoming from unexpected sources and potentially malicious outgoing traffic, or egress, can be blocked. This creates fine-grained, microservice-aware segmentation. It's dynamic, too. As pods scale or move, policies based on labels adapt automatically, unlike static firewall rules. They implemented these policies across their test, pre-production, and production environments, tailoring them slightly based on the specific front-end services used in each. This significantly reduces the blast radius if a single component is compromised. For engineers familiar with cloud infrastructure, you can think of network policies as being conceptually similar to security groups or network ACLs, but applied dynamically and specifically to Kubernetes workloads based on their identity via labels, rather than just static IP ranges. The second pillar of their strategy is Open Policy Agent, or OPA, specifically using the OPA Gatekeeper project, which is designed for Kubernetes integration. If network policies control network traffic flow between pods, OPA Gatekeeper controls what resources are allowed to exist in the cluster and what configuration they must have. OPA is a general-purpose policy engine that lets you define policy as code using a declarative language called Rego. Gatekeeper acts as a Kubernetes validating admission controller. This means that whenever you try to create, update, or delete a Kubernetes object, like a pod, deployment, or service, the request goes through the Kubernetes API server, hits the admission control chain, and is intercepted by Gatekeeper. Gatekeeper then evaluates the request against the custom policies defined in Rego. If the request violates a policy, Gatekeeper rejects it before the object is ever persisted to etcd, the cluster's distributed key-value store. This is incredibly powerful for enforcing security best practices, compliance rules, and organizational standards proactively. The CMS team didn't have to write all their policies from scratch. They leveraged a community library of pre-built OPA Gatekeeper constraint templates, and then instantiated them with specific parameters for their environment. Some key examples they implemented include allowed repos, which restricts container images to only be pulled from trusted registries like their official CERN registry, preventing accidental or malicious deployment of untrusted images. Container limits and container requests ensure that pods define resource limits and requests for CPU and memory within acceptable ranges, preventing resource exhaustion and improving cluster stability. Required probes mandates that pods configure readiness and liveness probes, ensuring Kubernetes knows when a service is truly healthy and ready to serve traffic, crucial for reliable deployments and zero downtime updates. Policies like disallow anonymous prevent binding roles to unauthenticated users, and replica limits control the scaling range for deployments. Think of OPA Gatekeeper like a superpowered linter or a pre-commit hook for your Kubernetes manifests, but enforced server-side at the API level. It prevents misconfigurations and enforces guardrails automatically. One potential concern with such systems is the overhead of managing policies. The paper highlights that they used Helm, the Kubernetes package manager, to package and deploy their OPA policies. This allows them to manage the policies as code, version them, and roll them out consistently across their different environments using a single command line interface, which helps manage the operational complexity. Gatekeeper also includes an audit function to check existing resources against policies, helping to identify and remediate non-compliant resources without immediately blocking deployments, smoothing the adoption process. The third key component is HashiCorp Vault for secrets management. We mentioned earlier that native Kubernetes secrets are just base 64 encoded and static. Vault provides a centralized, secure, and dynamic way to manage sensitive data like API keys, passwords, database credentials, and TLS certificates. The CMS team deployed Vault as a standalone server within the cluster using a Helm chart provided by HashiCorp, configured with persistent storage from OpenStack to ensure data durability. Crucially, they configured Kubernetes itself as an authentication method for Vault. This means applications running in Kubernetes can authenticate to Vault using their Kubernetes service account token. Vault policies can then grant fine-grained access to specific secrets based on the authenticated service account and namespace. Now, how do applications actually get these secrets from Vault? Rewriting every application to be Vault-aware using its API or SDKs would be a massive undertaking. Instead, the CMS team employed a clever pattern using the Vault Agent Injector. This uses a Kubernetes mutating admission webhook, similar in concept to OPA Gatekeeper, but modifying requests instead of just validating. When a pod is created with specific annotations, the injector automatically adds two containers to the pod specification: a Vault Agent Init container, which runs first to fetch the initial secrets, and a Vault Agent Sidecar container. This sidecar authenticates to Vault using the pod's service account token, retrieves the secrets the application is authorized to access, and writes them to a shared memory volume mounted into the pod. The main application container can then simply read the secrets from this shared volume as if they were files on disk. The sidecar agent also handles automatically renewing Vault tokens and refreshing secrets if they change or expire. This sidecar pattern is brilliant because it allows existing applications to consume secrets securely from Vault without requiring any code changes. The application remains blissfully unaware of Vault's existence. The paper details a script they created to streamline the process of creating secrets in Vault, especially when secrets originate from files. The script takes the namespace, service name, and file path, copies the files into the Vault pod temporarily, creates a key-value secret using Vault's KVV2 engine, generates a Vault policy granting read access to that specific secret path, and creates a Vault role binding that policy to the application's Kubernetes service account. The developer then just needs to add the correct annotations to their deployment manifest to enable the injection. While the paper focuses on the KVV2 engine for storing existing secrets, Vault's capability for dynamic secrets, generating short-lived credentials on demand for databases or cloud platforms, is a significant advantage over static Kubernetes secrets, potentially further enhancing security by minimizing the lifetime of credentials, although the extent of their current use of this specific feature isn't fully detailed in the paper. The integration provides encryption, centralized management, strict access control based on application identity, and audit logging for all secret access, a huge leap forward from basic Kubernetes secrets. So what are the key takeaways here? The CMS team demonstrates a practical and effective layered security approach for Kubernetes. Network policies provide network-level isolation, preventing lateral movement. OPA Gatekeeper enforces configuration best practices and security guardrails at the API level, preventing non-compliant or insecure resources from entering the cluster. Vault provides robust, centralized, and encrypted secrets management, decoupling secrets from application code and configuration. These three tools work together, each covering a different aspect of cluster security. The significance for us as engineers is multifold. First, it validates the power of these specific, widely used cloud-native tools for securing complex, critical infrastructure. These aren't bespoke CERN solutions. They are tools many organizations are adopting. Second, it highlights the importance of a layered defense. No single tool solves all security problems. Combining network controls, policy enforcement, and secrets management provides much stronger protection. Third, the paper emphasizes practical implementation details that matter for adoption. Using Helm to manage OPA policies and Vault deployments simplifies configuration across multiple environments. Employing the Vault Agent Injector sidecar avoids costly application refactoring, making secure secrets management much easier to integrate. This approach doesn't just protect against malicious attacks. It also helps prevent accidental misconfigurations, like deploying an image from the wrong repository or forgetting resource limits, which can significantly improve cluster stability and reliability, addressing potential operational issues beyond pure security threats. While integrating and managing three distinct systems undoubtedly adds operational overhead compared to default Kubernetes, the enhanced security, reliability, and compliance achieved are clearly deemed essential for a critical system like CMS WEB. The use of automation via Helm and patterns like the Agent Injector helps mitigate some of that complexity. In conclusion, the work at CERN's CMS WEB provides a valuable case study. By strategically implementing network policies, OPA Gatekeeper, and HashiCorp Vault, they've built a robust, multi-layered security infrastructure for their vital Kubernetes cluster, showcasing how these cloud-native tools can be effectively combined to protect critical services and data in demanding, real-world environments. It's a testament to how proactive security measures, leveraging the right tools and patterns, are essential for running reliable and trustworthy systems at scale. That's all for this episode of Podcast V0.1, and remember to never stop learning.